Hello and welcome to our lecture on Module 2, Single Area OSPF Configuration, in particular OSPF version 2 configuration. My name is Kelly Calder. I'm the lead instructor at Stanley Community College's Instructor Training Center. I want to go ahead and give you a warning beforehand. This is what I call a good enough lecture. In other words, I don't try to make my videos perfect. I would not be perfect if you were sitting in a classroom with me and I was standing in front of you, so I'm not going to try to be perfect in an online environment where I'm doing lectures. So if I misspeak, do ahs, whatever, just apologize. If the phone rings, I'll pause it and we'll go from there, but just be aware. We're going to take a look today at how you configure OSPF version 2. We're going to look at an item I've already discussed in my first lecture on concepts of OSPF, and that is router ID and how router ID is configured or set on a router for OSPF. We're going to look at point-to-point versus multi-access OSPF networks and how configurations, while very, very similar, have some different small, slight differences between them. Then we'll look at how to modify OSPF in single area environments and look at default route propagation, and then verifying it with our show commands that will allow us to verify OSPF. If you watched my first video on OSPF concepts, you will have seen a little short demonstration where I showed you a router with no IP addresses on it, either on its loopbacks, no IP addresses on its physical interfaces, and also no router ID set. And I tried to do a router OSPF and give it a process ID. We got an error message that said it could not initialize OSPF. Well, that is because in OSPF, an OSPF router must have a router ID in order for the OSPF process to start. Now, one of the ways to think about this is if you've ever used or had a Windows machine, one of the things inside of Windows is a process ID or a PID. So let's see if I can actually give you an idea. So here's some running processes on my machine right now. So my Zoom meeting here would have a process ID associated with it. Now, I don't have those process IDs showing here, but let's see if I can look at, see, app history. Nope, not there. Options. See, processes. I probably won't be able to find it inside of here because I'm doing this in the middle of a lecture and she'll look it up beforehand. But typically we can, and I could drill down in here and find the process ID for this particular process. Let's go over here. Oops, sorry. Go over here so I can't find it. So each one of these has a process ID associated with it. The exact same thing is going on inside of the router with OSPF. OSPF is a process running on the router. Okay, folks, so I was mad at myself, so I paused the video to go look it up. But you right-click inside of the name, and you can actually do the PID here, and that'll add the PID. So, sorry, I don't know why they don't show the PID to begin with, but here's the process ID. So Zoom on my machine is running under the process 33004, so 33,004. Exactly the same would be on a router. The router has to have some way to associate the process, and the process is associated with the router ID. So inside of OSPF, we need a router ID. The router ID is a 32-bit number. We're talking about OSPF version 2, which is the version used with IPv4. But inside of OSPF version 3, there's also a router ID, and the router ID is still a 32-bit value. So think about that. It's still a 32-bit or an IPv4 address. In order of precedence, if you set the router ID explicitly, in other words, use the router ID command under the OSPF process, that will be the router ID of the router. It will override any other things that are configured on the router. If you don't explicitly configure it, it's going to be the highest IPv4 loopback address. And if that is not configured, it will be the highest IP address on any physical interface. Now think, the problem with using a physical interface is if all the interfaces go down, there will then no longer be an IP address available for the router ID. So it's a best practice to, at a minimum, set a loopback IP address as your router ID. But honestly, the best practice is just manually configure your router IDs so that if the router's loopbacks are removed for some reason or the physical interfaces go down, you will still have a router ID. Now, configuring loopbacks, very easy. You can just go to interface loopback, put an IP address on it. These are 32-bit masks, which means that's a single address on that interface. And then that would be your router ID. So that's one way to do it. You also can do it with the router ID command, and you just go in under the OSPF process. Now remember, this number is just a process ID. So even though all of these routers R1, 2, and 3 are going to be in area 0, they can have different process IDs. This is just how the router is tracking that particular process, a router OSPF process, on the router in memory. But here we've set it with a router ID of 1111, 11111, 4 ones, so 32-bit address. If you had a router and you had physical interfaces up and running, and the router ID is modified. So let's say we had it set to where it was using, we already had an ID of 10.10.11 because when we configured OSPF, this interface, the physical interface, was up and running, 10.10.11, which if we look up here, that would be the loopback 0 was already running or already configured and up. R1 would have picked that as its router ID, which we see right here. We got it set as 10.11. We then change we want to physically set the router ID, and we set it with the router ID command. Well, this will override the dynamically chosen, I call it dynamically, but it is the previously chosen router ID, but it will not do it automatically. You must actually clear the IP OSPF process, and then it will reload. Now, be aware, when you do this, you're going to lose all of your OSPF connectivity, and you're going to have to go through neighbor adjacency creation again. You got to exchange your databases. You're going to have to build your shortest path first. So on a production router, this is going to cause problems with data being routed. So be careful when you do this in a production environment. It's best to go ahead, and the very first thing you do is set the router ID, and then clear your processes and ensure the router ID you set is the one that's being used. Now, inside the curriculum, folks, we do have a new thing called syntax checkers. These syntax checkers are basically just little simulations. And so enter OSPF router configuration mode using process ID. So I could do router OSPF 10. There's a couple things you can't do here, though. You can't shorten commands, and you can't tab commands out. So be aware of that. If you don't know what a command is, you can always put show me, and it will show you what the command is, or you can reset it and go from there. So just be aware that these are just little syntax checkers that do force you to use the entire command instead of shortened versions. Okay. So once we have created or enabled OSPF, we have to tell the router to advertise our directly connected networks. Now, OSPF uses a couple different ways to do this, and they're talking here a little bit about the point-to-point OSPF networks, and we'll talk about multi-access networks. But either way, you've got to advertise the directly connected networks. You'll notice the command is network address, a wildcard mask, and I'm gonna let you in on a little secret. If you actually put in the subnet mask, OSPF will convert it to a wildcard mask. However, on the exam, always use the wildcard mask. So real world, I tell people there's two different worlds. There's the real world and there's the book world. In the real world, you can put in the subnet mask, and it will typically, depending on the iOS version, that's something you do need to check, it will convert it to a wildcard mask for you. But on the exam world, you better put in the wildcard mask, or they're going to count it as being incorrect. This area is to associate this particular network with an area ID, and in our situation, we talked about multi-area OSPF slightly in our previous lecture, but our area will be area 0 for all of our CCNA examples. So what I want to do is look at how we can do this. So what is a wildcard mask? Wildcard mask is called an inverse mask. In other words, it is the opposite of a subnet mask. So if you've got, pull up Notepad here. If you've got a subnet mask of 255.255.0.0, a wildcard mask takes all the ones in the mask and turns them into zeros. So 255, which would be 1, 2, 3, 4, 5, 6, 7, 8, becomes 1, 2, 3, 4, 5, 6, 7, 8. So you get 0 in the first octet, 0 in the second octet. Now in the third octet, you'll notice these are all zeros. So we would convert them to all ones, which would be 255.255. So the wildcard mask for 255.255.0.0 is 0, 0, 255.255. Another easy way to do this, folks, is to take your wildcard mask or your subnet mask, whatever it happens to be. So it's 255.255. In this case, let's do 255.0, and just subtract it from 255, 255, 255.255. So in this case, we'd have 0, 0, 0.255. And this is the wildcard mask for this subnet mask. So pretty easy to do, not difficult at all, but just something to be aware of as you work in OSPF. So we're going to use our network command now. In this particular network we have here, we have R1 has, if we did want to actually advertise the loopback, we need to have 3 network statements. We would need to take on R1, we need to advertise the 10 network that is on the loopback. We'd want to advertise the gig 000 and gig 001. By the way, in our interior gateway protocols, which again, another concept covered in my previous lecture, in interior gateway protocols, we advertise only directly connected networks. You don't advertise routes that you don't know how to get to. So the router needs to advertise only directly connected networks. So using this command, router OSPF10, so that turns it on. We should have already set our router ID somewhere. We take and we put a network statement in for our loopback network, a network statement in for the shared /30 between R1 and R2, and a network statement in for the shared /30 between R1 and R3. You'll notice here, the mask on these links are 255, 255, 255, 252. So the wildcard mask is 000.3. Okay. There's another way to do this. You can go in and just use quad 0. If you do that, if you do the IP address and you do the interface, so in other words 10, 10, 1, 1, and do quad 0, area 0, this says advertise that network that is on that interface. There's another pretty neat thing you can do. You can do all quad 0s and 255 and it will advertise all networks on an interface. So I want to bounce over to NetLabs. This is what we use at Stanley Community College. This is real gear in labs that we use to show examples, and also it's where our students do their labs for our online classes. So I'm going to R1. I've already done some basic configuration on R1, nothing major, but I just did a show IP int brief. And you'll notice that I've got on my gig 001, I've got a 192.168.12.0 network /24, and I could do a show int GI 001. And you'll see that I've got a /24-bit mask on the inside, which, by the way, that is this network right here down to PCA. And then on my other network, on my other 0, which is across to R2 point-to-point link, you'll see I got 10.001/30. So I'm going to configure OSPF. So I'm going to do router, got to go in global config first, config T, router OSPF 1, just process ID, router ID 1111. Now I'm going to do a do clear IP OSPF process just to ensure that I get the right do show IP protocol. You'll say make sure I get my right router ID, which in this case is 1.1.1.1. So I did that. Now I need to put in a network statement for the 2 networks I have. So I have the network 10.0.0/30 and 192.168.12.0/24. So I'm going to put in 2 network statements. Network 10.0.0.0, 0.0.0.3, area 0. Then I'll put in another network statement, which is, by the way, I'm just using tab to tab that out, 192.168.12.0, 0.0.0.255, because it was a /24-bit mask, area 0. Okay. And let's do a do show IP int brief and make sure I didn't forget to not bring them up. And they're both up, so we're good there. So let's move over to R2. Now we're going to configure R2 a little bit differently. We're going to go and do, by the way, if I do a show IP int brief, you'll see that on the gig 000, which is the shared network between R1 and R2, you'll see I've got the 10.0.0.2, the other part of the /30, and I've got 172.16.0.0, and this is a /16 on this. I'm going to do config T. I'm going to do router OSPF, just one again, that's process ID, router ID of 2.2.2.2. I'm going to do show IP prot, and let's see if it's got the right. It did take the right router ID, which is 2.2.2.2. And I'm going to make a different network statement. I'm going to do network 0.0.0.255.255.255.255 area 0. And if I do a do show IP protocol, you will see that it's actually advertising for all networks. Now, I can actually now do a do show IP route. By the way, do just lets you run commands inside of configuration mode that are not meant to be there. And you'll see that I've got this OSPF route from my R1. If I go to R1 and do a do show IP route, you'll see the 172.16 network from coming over from R2. The cool thing about what I did on R2 is if I go into R2 and I go to interface, interface LO0. So if I add another network, let's say I had to add a network somehow, and I did IP add, let's just do 204.211.19.1, 255.255.255.0. Okay. Now, one of the things you'll notice is I go back over here and run another do show IP route shortly, shouldn't take it too long. I should get another route to 204.211.19.1, and I made no changes to my OSPF configuration because I had told it every network on this particular router advertise it. Now, the only thing about that is you need to be absolutely sure when you use this command that you want every network to be advertised into area 0. Otherwise, you're in trouble. So it's a shortcut. It's not shown in the curriculum. It's something I wanted to show you. But at this point, if we do a Control Z, I do a do show IP. Oh, I do a do now because I'm not in configuration mode. Show IP OSPF neighbors. You'll see my neighbor is 2.2.2.2. Show IP protocol. You'll see that R1 is advertising the networks 10.0.0.0/30 and 192.168.12.0/24. And if I do a show IP route, you'll see that I'm getting the 72.16 network from R2 and the 204.211.19.1. Now notice, since I'm only advertising these two and I use a very precise network statement, if I added another network to R1, so if I did config T, interface loopback 0, let's say I did the IP add 131.107.0.1, 255.255.0.0, that will not automatically, if I do a do show IP protocol here, that's not going to be advertised. So I've got nothing here to automatically advertise that, and I'm not going to see it over here on R2 because there's no network statement for the 131.107 network. If I go back into R1 though, go back into OSPF. And folks, I apologize for my typing sometimes. I was actually, believe it or not, hit by a truck 4 years ago and paralyzed from the neck down, and I don't type as well as I used to. I'm not paralyzed from the neck down anymore, but I still don't have full use of my hands. Okay, so now we've added this network. So I'll do a do show IP protocol. You'll see now that I've got the network statement for the 131 network. And now if I go over to R2, up arrow, we now see an OSPF route from R1 for 131.107. So the network statements are used to advertise your directly connected networks, and there's multiple ways of doing it. The network statement is one way. There's another way to do it too. you can use the OSPF command. So if you could remove all of these statements. So let's go back into R1. And I'm going to remove no network 10.0.0.00003 area 0. By the way, this is going to break our entire OSPF neighbor adjacency because we're not routing for the network between R1 and R2. But I can now go, because you see here, gig 001. Okay, we're going to use the command to use OSPF area and tell it what area to be in. So you got to have the process ID in the area. So let's go back in here to gig 000. We're not advertising that network right now, not advertising the 10 network. We can go to int gi 000 IP OSPF 1 area 0. And now, see, we've now got an adjacency. Go back to R2. We've got, should have all our routes back in here. Yep, and we do. So we got all our routes back in from OSPF. So we've got 131.107. We got the 192. And so we just used a different method. And when you do a show IP protocol, you will see that we're routing for these two networks using network statements, and this one using the interface. Now this is a cool command if you have to ever change IP addresses on an interface, because that will allow it for you not to have to change your network statements because there's no network statement. It's just using the interface. So that's another way to do it. Another thing we have here is what's called a passive interface. Now, one of the things that happens with OSPF is it does send out hello packets every 10 seconds on all the configured interfaces. Well, if you're looking here at our network, R1, there's nothing on the loopback that needs to have any kind of hello packets going out. So that's a waste of bandwidth, it's a waste of resources. It's also a security issue because someone could grab those hello packets and learn more about your network. So you can actually make a passive interface. And when you do that, it will no longer send out routing messages through that interface. Now, it will still allow it to be advertised, but it just won't send out its hello packets and LS, link state advertisements, link state database packets and all won't go out L0. So that's what the passive is for. So we get a passive interface, loopback 0. Notice that is under OSPF configuration. It is not on the interface, which is a little bit weird. So now, we talked a little bit in chapter 1 or module 1, excuse me, about OSPF in multi-area networks. So the ability to do BDRs and DRs to limit the number of adjacencies that are necessary. You will notice that even in my network here, all right, where we have only 2 routers across this R1, R2, if we go in here, you'll notice that if I go, sorry, click on the wrong button, Control Z, I do a show IP OSPF interface GI 000. You will see that this is the designated router is 2222. This router is a BDR. Now, in other words, even though this is a point-to-point link with no other routers on it, because it's Ethernet, OSPF does a DR-BDR election. Now you can change that behavior. You can go into the interface and make it a point-to-point OSPF link. It's very important though, if you do this, that you do it on both sides. So you can see here again in R1, R1 is the BDR, R2 is the DR. So I'm gonna do a Control C here, config T, and GI 0/0/0. I'm going to do I'm going to do IP OSPF type interface. Well, I've forgotten the command, folks. Network, network, point to point. Okay, hit enter. Now you'll notice we're getting a problem here. We got to go over to R2 and go to int GI 0/0/0. 0, IP OSPF network point to point, hit enter. And then now, if we do a show IP OSPF interface GI 0, 0, 0 on R2, you'll notice this is now a point-to-point link, so there's no DR, BDR, because it's point-to-point. Same thing on R1, Control Z here. Do that same thing, and you're going to see that this is now a point-to-point link, which makes sense because there's nothing else here. So you don't need a DR, BDR election across this link. You can do the same thing with loopbacks, because if you look at a loopback, obviously there's nothing else on the loopback out here. So you can make those point-to-points, and you can also just make them passive. Okay. Now, on our multi-access networks, these are the networks that are attached to Ethernet, and we have ability to do broadcasts on them. So in these networks, we're going to have designated router elections. By default, the routers send out their LSAs to 224.0.0.5, which is all OSPF routers. With a DR, you have 224.0.0.6, and that is the DR and BDR. So when I send an LSA from a router on a multi-access network like Ethernet, instead of sending it out to everybody, I send it to 224.0.0.6, or the router does. That goes up to the DR and the BDR. They then take those LSAs and send them out to everyone else using 224.0.0.5. This keeps the routers from having to all form adjacencies with each other, as they only form adjacencies with the DR and the BDR. Again, making less flooding of LSAs, more efficient use of bandwidth, and it's an overall more efficient network. Now, looking at our router here, when we do election of the DR, the router with the highest priority on the link will be the designated router. However, by default, all link priorities are 1. So the next item in line is all the highest router ID. The highest router OSPF router ID will become the DR. In our case here with this particular network, all priorities are the same, so they're all 1. So router 3 with the ID of 3333 would become the DR. The R2 with a router ID of 2222 would become your backup designated router. And then R1, as long as the priority had not been set to 0 on gig 000, would be the druther, or a possible DR BDR if one of these others fail. Now, you can look at the role by looking at R1 and saying show IP OSPF interface gig 000, and you'll see that this router is a druther. In other words, it's not a BDR, it's not a DR, but it could become a DR or a BDR. You can see the priority is set to 1. By the way, if you did not want R1 to ever become a DR or BDR, set its priority to 0. If you wanted to make sure that R1 became the DR, set its priority to something higher than 1, and make sure it's higher than any other priority set on the other routers. R2 is the BDR, okay, and then R3, because it has the highest router ID, is the DR. So you click show IP OSPF interface and then the interface, and you can find out what is the DR, BDR, and druthers for that particular network. This slide really, or section really just talks about the fact that if you have full, that is what you should see. That means you've got a full adjacency established. Two-way druther is also a state that can be in effect if the routers have a neighbor relationship with a non-DR, BDR router. Okay. So here's our election process. Again, we're going to look at router, the OSPF priority on the interfaces. If that is not set to anything other than the default of 1, we look at the highest router ID, and that just goes to the normal router ID. So Is it configured manually? Is there a loopback IP address? Is there a physical address? So you take your router ID. Now, with DR and BDRs, DRs can fail. And if they do, the BDR becomes the DR. And then there's an election so that another router that has the ability to can become the BDR. You'll notice the negative, though, is when R3 comes back online, it does not automatically take over as the DR again. It stays as a druther until you have R2 fail, and then you'd have R1 become the BDR or the DR, and R4, if it joins the network, by the way, R4 would still be a druther. So basically what happens is if a router is in a particular mode of DR or BDR or druther, even if another router joins with a higher priority or router ID, it will not take back over. Now, OSPF is a better way, OSPF priority is a better way of doing this than using your router IDs. So with this, you go into your interfaces and you set a value between 1 and 255, 255 being the highest. And that will force that router to be the DR once you clear the process, okay? Now, you also can say make R3's interface a 0, and that will mean R3 will never become the DR. Why would you want to do this? Well, you may want, let's imagine R1 is in your core, R2 is at another building, and R3 is in another building. So you want the DR to be in your core because that's the router you trust the most to have the capacity to handle it. That is why you would set its priority to the highest level. And then that will be your DR on the link. And then you can also configure the BDR with the next highest priority, and then any router you don't want to be one has a priority of 0. Okay. Now, one of the things about OSPF that's a little weird, and it's not really weird, but it's a little different, is that it uses cost. It uses a metric called cost, which is based upon the bandwidth of the links. And the default reference is 10 to the 8. So it's interface bandwidth in bits per second. And the negative of that is that a 10 gigabit and a 1 gigabit link using the default reference cost both have a cost of 1. So to OSPF, a 10 gig link and a 1 gig link look the same. Now, we can change this. You can change, in fact, anything above 100 megabits ends up being the same. You can change the cost, the auto reference cost. So we can do auto reference cost bandwidth in megabits. So we do 1,000 for a gigabit and 10,000 for a 10 gig. You can set it up so that you, by the way, 10 gig would be, that would be for setting it to allow for 10 gig to have a cost of 1, gigabit cost of 10, fast 100, and Ethernet of 10 megabit of 1,000. The only thing I'll warn you about is be careful, because in many of our networks today, 10 gig is not even close to the fastest links we have. For instance, in the data center we run, we have 40 gig links and we have 100 gig links. So you may need to change those auto cost reference bandwidths. The other thing that you need to be aware of, but we're not running OSPF in our data center, quite honestly, we run layer 2 for speed. But the other thing you want to be careful with is if you change the auto cost reference bandwidth, you must change it on every single router in your network. Otherwise, your routers will be creating their shortest path first cost pass using a different reference bandwidth, which can cause some very, very weird routing issues. So accumulating costs. So if we want to get to a particular link, so if R1 wanted to get over to loopback 0, the cost would be, the shortest path would be a cost of 11, which is 10 and 1, instead of going 10, 20, 21. And so cost and the path uses the complete path, including the destination network as part of the cost. Now you can set the cost if you want to, so you can literally go in if you want to change it. You really need a good reason to do this. You may want to, if you want to try to control traffic going a certain way, or if vendors are using some different calculation for OSPF's auto reference costs, you may want to do that. I would not make changes to my costs unless there was an extremely good reason to do so. Here we are testing a backup route. The other thing you can change as far as on OSPF is its hello interval. Again, only change this if you're told to do this for a very particular reason. Typically, it'd be something that tax support would tell you to do. But if you don't set the hello and dead intervals to be the same on all your routers in your network, it will not work correctly. So when you go changing these, make sure you change them on every router in the network, or they won't form neighbor adjacencies with one another. One of the last major things we want to look at with OSPF single area configuration is how do you propagate a default route into OSPF. It's really very simple. Let's imagine that R2 is our border router with the internet. And so we have a static route using the IP route quad 0, next hop address or exit interface. We put that on R2. So we're saying to get to the internet, go out, loop back 0. I know that's a simulated internet connection, but just tell it to go out, loop back 0. You then go into OSPF on R2 and put in default information originate. This tells R2 to advertise an external route, an external default route, propagate that internally. So in R2, you'll see we've got our static route going out, loop back 0. We've done default information originate on R2. On R1, you'll see there's an OE2. So in other words, there's an OE2 external route. By the way, this is because of the type of LSA it was brought in on. It says this is an external route that says the default route is available via 10116. So it's going to say on R1, for me to get to the internet or to get out to anything I don't already have a route to, go up to R2 and let R2 handle it. R2's got the default route to handle it. On R3, though, you'll see that it says OE2 quad 0 via 10119. So it says go up this direction to R2. So it's not saying go over to R1, it's saying go to R2. So R2 has the static route, default route on it. And with the default information originate, R2 will then propagate the default route down. And by the way, that would be propagated to any other router that's running OSPF below R1 that's in the same area. So all of these will be propagated and actually can be propagated between areas. So pretty simple. Last but not least, we've used these commands, but let's run through them again. Show IP in brief to show that your IP addresses are on your interfaces and they are running and up. Show IP route to find your routes. Show IP OSPF neighbor shows your OSPF neighbors. Show IP protocol shows your OSPF configuration. Show IP OSPF, we can do that in here. Click in here. Show IP OSPF. You'll see it tells you the information about it, writing process, tells you the hold times, tells you the database summary, shows you the areas that this particular router is in and what interfaces are in it, tells you the checksum on the LSAs, large amount of things inside of that show IP OSPF. And then we know the show IP OSPF interface is where we can find our DRs, BDRs, and the hello and dead intervals that are set. And I believe, folks, that is pretty much it for Module 2, Single Area OSPF Configuration. I hope this has been useful, and I hope it will get you started on your configuration of OSPF version 2 in a single area.